Hello all, welcome to my channel. Back with a new video. This is a new series that we are doing on newer Lakehouse technologies. We have already done one with Apache Plus. Now we will be discussing in this blog Apache Paimon or Paimon, um, depending upon how you pronounce it. I like it to call Apache Paimon. Uh, so let's get started and see what it is and why we need this. So in Lakehouse, we have a lot of other options as well. Like we have file formats like Iceberg, Hoodie, Delta, and Hoodie was pretty much good at doing streaming workloads. So why did we create another table format for Paimon? Uh, the reason for this was this project was started. This was started as part of a project where we wanted a storage option for real-time streaming, mainly Flink. So it if we can say that we wanted an streaming application on the Lakehouse rather than doing on uh, the system which has its aggregated or coupled storage. So Apache Paimon provides a streaming storage layer and extends Flink's capability to do stream processing directly on the data lake. So earlier we had, for example, we had Spark, which was doing analytics on the Lakehouse. We had other engines. So there was no engine as of now which was doing streaming workloads on data lake because most of the formats were not designed for a streaming use case. That's the gap that Paimon is trying to fill, and it started with Flink because Flink is the default stream processing engine as of now. So Paimon supports streaming workloads on Lakehouse, and that's what the trend is called now, Streamhouse, which is nothing but streaming plus Lakehouse. And some of the key capabilities of Apache Paimon is it supports both streaming and batch workloads. It can handle stream updates, batch reads and writes, and change log generation in a unified platform. It has the data lake capabilities, like it's a lakehouse solution. It is completely on object storage. It has different engines that it supports. Like it can use Flink engine, it can use Spark engine uh, to do certain merge aggregations. It has support for real-time aggregation. It gives change log generation, rich table types, supports time travel, merge on write and copy on write. Both options are supported. And this supports automatic compaction, automated expiration of partitions, and automated expiration of snapshots. So the table maintenance is baked into the platform itself. And Paimon is built for speed and treats Flink as a first-class citizen. So this is what at an very high level what Paimon is, and Paimon has different elements or different components into it. Like one is the open data format. So Paimon uses file formats such as Parquet, ORC, and Avro to store the data. It has large-scale real-time capabilities because it integrates with Flink CDC and can do real-time updates. It has partial table update capability because it has a concept of a primary key table. If you might have seen my last video on Flux, that also has primary key at table type. This is getting inspired from Flux itself. Then we have stream batch integrated data entity, like one engine which have both streaming and batch capability. Paimon can also be used as an Kafka replacement, not full-fledged, but yes, at certain places where we don't have that much of high latency requirement, we can replace Kafka with the table type. We can say primary key or append only, and in Paimon, and that will act as a message queue because it has the support for CDC. So what becomes is whenever we update a record, a new CDC event will be generated, and the downstream engine, for example, Flink, can consume it. So that makes it one what you call loosely saying Kafka system which is present that can be used. The entire file layout is similar to Apache Iceberg, where we have snapshots. I mean, in Iceberg we have snapshots which are composed of manifest list, and then the manifest list is contains information about the manifest itself. Manifest points to certain data location, data files, and then certain delete vectors and other things. In this case, manifest is determined by the bucket, and uh, that bucket has a corresponding LSM tree structure which is present as a data file. So this is, for example, for Paimon, we have this, like same as Iceberg, we have snapshot pointing to a schema, then we have base manifest list and delta manifest list. Each of the manifests do point it to the data files. And if you see the table structure, in the table layout in a folder structure, then you will have table, then you have buckets. Inside bucket, you have data files. For the table, you have an index, you have manifest, you have schema, and you have snapshots. So this is how a table is organized in Paimon, which is pretty much similar to how uh, Iceberg stores the data. Snapshots is the schema recorded as a JSON file. Whenever it changes, the included field information, partition key, PKN, primary key, and table option informations are also updated. Manifest list is an Avro format file containing the meta information about the manifest files. Then this also supports, similar to Iceberg v3, this says Paimon has support for deletion vector. Uh, Paimon distinguishes itself as the only lake format successfully combining the LSN tree technology with the data lake storage paradigms. And this combination delivers the right performance characteristic of a real-time databases while maintaining the data lake scalability and cost effectiveness. So that's why we are saying this is a Streamhouse kind of a solution, because it allows us to do faster writes, updates, as well as it scales infinitely because it is powered by the object storage system. When a payment table is configured with Iceberg compatibility, the system automatically generates the Iceberg snapshots, including the real-time data files with corresponding deletion vectors. And that's how we have offloading of Paimon from Paimon table format to Iceberg table format, so that that data can also be consumed by other engines which are very much comfortable with Iceberg. So because Paimon is new, there are not many engines which are supporting their consumption from their engine. For example, as of now, a lot of other databases are there which do not support Paimon table format. They support Iceberg. So what this offloading, what we are doing, that okay, if we are able to generate a corresponding Iceberg table as well, with data files being pointed with less copy of data, that actually helps us in making Paimon's usability go up, because we will have more and more engines which can read and understand the table format which is there. So this is about uh, the Iceberg integration. Table types, as we have, as I mentioned as well, like it is similar to how Flask is doing. It has two types of table: primary key table and append table. The primary key table can be of two types. One is fixed bucket table, and another one is dynamic bucket table. So in the dynamic bucket tables as well, we will have normal dynamic buckets, and then we will have cross partition update table. So these are so the difference is, in dynamic fixed bucket tables, we will have a default bucket count set to 1, and then we'll have to provide a bucket count which is greater than 0 in case we want a fixed bucket table. But in case of dynamic bucket tables, the number of buckets is set to -1. So the size is the number of buckets is decided dynamically, not fixed. So primary key does not contain partition field. If it does not contain the partition field, then it will have a cross partition update table. But if primary key contains the partition fields, then it will have normal dynamic bucket, which is automatically buckets maintains the bucket number based on the primary key which are present, and it has also a memory in-memory index. In case of crosspart, there is the index is stored in the rocksdb for us. So this is some different types of tables which are there. And then append only, again, we have concept of fixed bucket versus, let's say, which is called an append only queue table. if we have fixed number of buckets. But if we don't have fixed number of buckets, then we say append scalable table, which keep on increasing, and it will have this is a replacement for an hive table, and it will have option of allowing z order sorting. In case of append only, it has an order by the bucket key. If we mention the bucket key, it will be ordered by that. So this is these are the different table types which are present in Paimon. uh, the primary key table is the one which allows it to do real-time streaming workload, because it supports insert, update, delete, and the primary key tables as partitioning. So what it does, it each bucket contains a specific LSM tree and its change log file. So based on that, it decides that okay, bucket is based on is they decide which part of the tree gets into the different run labels. So LSM tree has an different labels, and each label has certain SS table that gets merged. So that based on the key that is coming, it will decide which segment needs to be updated. And in general, the recommended bucket size is around 200 MB to 1 GB. So the fixed bucket primary key table has so the primary column and not infos plus bucket number, that is what we call is a fixed bucket key. Then we have normal dynamic cross part update table, and then other few, like for example the primary key supports the three table modes: copy on write, merge on read, and merge on write. So these are three different ways in which we can support the table updates. Append tables are which one means if we do not define any primary key on the table, then it becomes an append table, and it is the compaction of the append table is only used to merge small files. Currently, there are two modes. One is scalable table where the bucket count is not defined, and then we have queue table where the bucket is 10 and bucket key by is column name that we can give. Bucket 10 is this not that we have to stick to 10. We can give any number that we want, but yes, in general, we can have this as well. So now comes the merge engines. So the merge engine in Paimon is used to merge write data with the same component. Paimon mainly supports the following three merge modes: deduplicate, partial update, and aggregations. So these are the engines. So basically we say we can define these engines. And Paimon does automatic compaction. It waits for the similarly sized tables to converge before merging them together. And only one compaction task can be performed on the same partition within a table at a time, and conflicts may occur if tasks are executed concurrently. So this is one thing to note, that when to do compaction, the concept remains similar to how iceberg compaction works. So we have different compaction options like full compaction. We can do asynchronous compaction. We can do a record level expiration. We can do a lookup compaction. So there are different compaction modes that we can do, and they're similar to how uh, various strategies of partition pruning happens in Iceberg. Paimon supports a lot of partition pruning, bucket pruning, pruning based on min-max aggregate values in the manifest file. It also supports Bloom filter. So those strategies are still valid in Paimon as well. Paimon is multimodal. So multimodal in a sense means that we can have different file formats included in the Lakehouse. For example, Lance files format that we can use and the reason this has been made a choice to have multimodal support is because in the newer GenAI domain, we won't have one structured tabular data. We will have images, we will have PDFs, we will have different types of data which are not structured, and multimodal helps us in uh, getting data or getting insights out of it. Hence, this Paimon decided to support multimodal AI storage requirements, and hence its supports for Lance is very much important. It also is integrated with other AI focused processing engines like Apache Arrow and Ray. So we can consume the Paimon table in, let's say we have created a multimodal lakehouse, and we can consume that data set in Ray using Apache Arrow to do machine learning against Paimon stored multimodal data. So that's what where this is headed towards. Uh, Paimon is available. Paimon is being used at large corporations like TikTok, ByteDance, Alibaba. So and the companies which have supported these project as well, like um, I think Vivo also uses this. So a lot of uh, production usage is already there for Paimon. Now let's see Paimon in action. So in this blog, I also have one working solution where I was trying to see how we can consume Paimon with Trino. And so basically what we will do, we will process the data using Flink and make updates and see query it from two different engines. So we will see how quickly it becomes available. So some housekeeping or prerequisites that we have to do is we have to download the jars. So when I tested it, it was for Flink 1.19. So I downloaded this Paimon Trino jar because I want to query Paimon through Trino. That one is there. Then I want Flink to be working, so I downloaded Paimon Flink jar as well, which is for 1.19. This is Paimon Flink 1.19. This is Paimon Flink Action. Some jar is there. And then I downloaded the S3 jar for Paimon. So Paimon S3 jar also I downloaded. And Paimon Trino plugin, which is needed. So I downloaded these things. MariaDB I installed just for the what you call Presto part, Presto or Trino part. And then in the Trino catalog, I created the Paimon catalog. So the connector name is Paimon. I gave the virus, link location, and gave S3 region, everything. And these are, you can get it from Mini.io because I am using, instead of S3, AWS S3, I am using S3 compatible storage called Mini.io. So in Mini.io, it has S3 compatible API. So you provide this information from there. Then I created a Docker Compose file which will have three services running, one for Trino, one for Mini.io, and then we will have this is a dependency on Mini.io itself. So this also Mini.io client container that launch, and then we also launch in a StarRock's uh, engine to query this information. Then now I am creating a new file, Docker file, which will have the Flink jar as well as so this is coming from Flink base. And then I am putting the jars that I need for Iceberg, I need for Flink, I need for Paimon, Hadoop Common and everything. So all the things that is needed, I download it in this and then make the Docker files, Docker come up. When I bring this up, so here I think I have missed the Flink part. So Flink container is also running in here itself in the Docker Compose app. I will see where is that full file. And the Flink, when we run the Flink SQL, it comes up, and then I'm in from the Flink side, I will simply say that okay, I want to create a catalog with type Paimon. I created that catalog, then I created it's reset. So I created the catalog, then I created a table called word count, uh, and then I created another temporary table called word count table. Or this was there. Connector was data gen, so this will generate our data so that I can see the data in the query engine. Paimon requires checkpoint interval to be streaming mode, so I gave a 10-second in streaming interval, and then streaming. This was the from word table, which is the data generator, which is generating this data. I will insert into this word count table. So this table will generate data like word, and this will have word and count. It's count that we will see. So I will group by the word. This is what it will going into the word count table. So once we have this Flink job running and the data is generated, we will see it like this in the Flink UI that okay, source is word table, and then grouping constraint is there, and then it, dynamic bucket assigner is used, and then it will write to the global committer word count table. So this is the Flink running the job. And what we will do is we can query the Flink jobs like because it is we want to get the counts out of it. We simply run this set the result mode to tableau, and then we switch it to batch mode, and then query the count, olap query to count the query the table. So we will see like this, that we have word and how many times it has come. So 0, 1, 2, 3, A, B, C, D, E, F, there are 16 rows, and it returned in 3.76 seconds. The Flink SQL, we are querying from Flink SQL itself. Now, once the Flink starts to generate the data, and we can go to the menu IO and see the files which are getting in the Paimon layout. So I provided so this is the UI for Mini IO. So in Mini IO, you provide your username and password, whatever you have decided when you launched. Once you see that, you will see iceberg, you will see uh, bucket, index, schema, snapshot, and everything. And then you will see the data in here, that whatever is present in this. And if you create the external type Paimon and catalog type, we create a new catalog. In the star rocks SQL CLI, we create this table, and then we query that, okay, what is the count coming in here. So see, what is happening is data is getting inserted at a faster time. So here, let's say it was only 1,99,000. Here it became 2,74,000, because I was again, I created a new so the data is getting generated, and it is getting reflected in real time in Star Rocks. Same thing can be queried from, let's say, Trino. So the moment I logged in from Trino, I see the Paimon default word count table. If I query, I am getting a different count, which is again because the rows have been increasing constantly. Uh, so this was a demo that we can use to see how we can access the same table across different engines and process data using Flink. And then if I Flink, sorry, Paimon can also be integrated with Spark. So this is Paimon Spark integration. So Paimon supports version 4.x version of Spark, and 3.543 and 3.2 version of Spark. So for example, if we want to use Spark SQL, we can say Spark SQL, we provide certain other configuration, we pass the jar that we want to use, and then such configuration like the catalog and extension we provide. And then if we want a data frame to be written as a Paimon format, we give the option Paimon format, and then save it. And if we want to see it in Spark structured streaming, and if we want to see a tables, we want to get consume the data which are getting related to this Paimon table, we can simply say Spark read stream format pop Paimon, and then provide the location where we want to the table location is, and then we can trigger it as well. And if we want to persist the data, let's say we have a data which is data frame which is coming from some other source, and we want to persist into what you call Paimon's location, then that also we can do. We can provide the format as Paimon location and write the stream. So this is how Spark is also integrated with Paimon. Uh, so we have seen a lot of times we are comparing Paimon and Iceberg. The reason we have done this comparison is not all engines, as I mentioned, not all engines are supported as of now in Paimon. So Paimon is trying to be as of now to reduce the onboarding time or barrier to entry point. Paimon supports Iceberg integration, but there are some differences. For example, the primary use case for Paimon is streaming. In case of Iceberg, it is batch. Then storage format is Parquet and ORC. Similarly, here also is Parquet. Transaction, both of them support AC transactions, but only thing is it supports in batch mode, while Paimon supports in streaming and batch both. Schema evaluation is supported by both. Partitioning is also supported by both. Streaming support is optimized for real-time ingestion, Flink native, Paimon. In case of Iceberg, it is primarily batch, but supports streaming via external tools. Performance, the latency numbers are lower in case of streaming workloads for Paimon. Concurrency also, it uses optimistic concurrency control similar to what Iceberg does. Compaction strategy is streaming friendly, and compaction it happens on a regular interval using Flink itself. Batch, so in Iceberg it is in batch mode, and we have to trigger the compaction ourselves. Supported tools. It works best with Apache Flink, but also works with Spark. This one Iceberg is better suited for Spark, Presto, Trino, Hive, or Dremio. Community adoption, this is Paimon community is growing up. It is not, it is not a full-fledged project. I mean, it is full-fledged project, but it's not that user adoption is not that high as of now, but it is growing. Batch performance is adequate but optimized for streaming. This one is only for batch. Cost optimization because incremental data ingestion lapsing it reduces the cost. In case of this iceberg, the snapshots can get large and we'll have to do certain maintenance as well. So this is the summary of how Paimon integrates with different system, what it is, why we need this, and how it is different from iceberg. So if you like it, do share it, spread the word, and have a nice day.